So now we're going to do the disaccharide lactose. Remember with maltose, it was two glucoses and the glycosidic bond was an alpha 1,4 between the two glucoses. Lactose is made up of galactose and glucose, but the bond between the galactose and the glucose is a beta 1,4 glycosidic bond. So let me draw that out for you guys. This is galactose. We have galactose looks just like glucose. Remember, this is carbon 1, this is carbon 2, carbon 3, carbon 4. Remember, galactose, that's where it differs from glucose. So goes up, and then this is CH2OH, that's carbon 6. Now, carbon 1 of galactose is hooked up to carbon 4 of the glucose in a beta 1,4. So what I'm going to do is, this is a beta. Remember, if at carbon number 1, the OH is pointing up, it's a beta, so this is a beta. And draw this out. Here you go. So carbon number 4 of glucose, always the OH is pointing down, so this is why this is down. Carbon number 4 of galactose pointing up. This is carbon 2. This is carbon 3. So this is a glucose. This is a galactose. This right over here is a beta 1,4 glycosidic bond. Now, lactose, we can decide, do we want our lactose to be alpha lactose or beta lactose? What will determine that? Carbon 1 right over here, the one that is still the hemiacetal, that is not hooked up in the glycosidic bond. This is rigid. We're not touching this. This is always beta 1,4 in lactose. But this could be up, it would be a beta lactose, or it could be down, it would be an alpha lactose. So I'm just going to put it down. We have both, so let's just put this down. We look at this. This is called the anomeric carbon. It's the carbon that can easily open and become a potentially free aldehyde. So this right over here is alpha D lactose. And what is important about alpha D lactose, I mean, you could pretty much eliminate the D if you want to. What is important to know is that lactose is made up of galactose and glucose, and the bond between the two is a beta 1,4 bond. Okay? If you want to draw an alpha lactose, this OH has to be pointing down. If you want to draw a beta lactose, flip it, this OH is pointing up. Do you touch this? Absolutely not. Do you touch anything else? Absolutely not. The only thing you're allowed to flip up and down is this guy over here, carbon number 1 of the glucose. Okay? Now, the next disaccharide is Cellobiose. Cellobiose is a disaccharide made up of two glucoses, just like maltose was, but the difference is that Cellobiose has a beta 1,4 glycosidic bond between the two glucoses, not an alpha 1,4. Where do you find Cellobiose? That is a breakdown product of cellulose, which is a polysaccharide that makes up fiber. You know, when you're eating celery or any of the vegetables that you're supposed to be eating every day, obviously, to get your fiber, you're eating a bunch of cellulose. We don't have the enzymes that digest it. But Cellobiose is a disaccharide that if you put a whole bunch of them together, you end up with cellulose. This is Cellobiose. We're just going to draw a glucose. And this is carbon 2, carbon 3, carbon 4, carbon 5, and then carbon 6 is over here. Remember, this is the O that belongs to carbon 5. And we're going to do a beta 1,4 just like we did with lactose. So here we go. Here's the other glucose. And carbon 2, carbon 3. Carbon 4 of this glucose is hooked up with carbon 1 of this glucose. And you can recognize that this bond is also a beta 1,4 glycosidic bond. Now, do we want Cellobiose to be alpha or beta? Either one. If we put the OH up here, it becomes beta cellobiose. If we put the OH down at carbon 1, it's alpha cellobiose. So let's just go ahead and do this. And so notice at carbon 1, it's going up, so therefore this is the beta. So this would be beta D-cellobiose. Okay? So you see how it differs from maltose. Maltose is also 2 glucoses, but the glycosidic bond is alpha 1,4. Cellobiose, 2 glucoses, but the glycosidic bond is beta 1,4. All right, the last disaccharide we're going to be doing is sucrose. Sucrose is table sugar. You get it from sugar beets and sugar cane. Sucrose is made up of glucose and fructose. But the interesting thing about sucrose is that the way those two monosaccharides are bonded together, you are hooking up the potentially free aldehyde and the potentially free ketone in the glycosidic bond. So you don't have a hemiacetal that is available to flip and become alpha and beta. And this becomes important when we start talking about chemical reactions because sucrose can't be oxidized the way all the other disaccharides and monosaccharides can because it doesn't have that potentially free aldehyde. It's all hooked up in the glycosidic bond. So when we get to that section about chemical reactions, we call sucrose a non-reducing sugar, meaning it can't be oxidized and it won't reduce an oxidizing agent. Okay, we'll get to that in a bit more detail later on. Anyway, so the way I like to draw sucrose, I put a glucose on top and I put a fructose on the bottom. I put an alpha glucose on the top and I put a beta fructose on the bottom. So this is my structure for sucrose. I found this makes it a little easier to see. All right, so this is it's going to be an alpha, so it's going to go down. All right, I'm going to have a bond. So this is an alpha with the glucose. Now with the fructose, remember it's going to be carbon number 2 that determines alpha and beta. So this is carbon 1 is outside of the ring. Remember with fructose, carbon 1 is outside of the ring. Carbon 6 is outside of the ring. So this is carbon 1. This is carbon 2. Carbon 2 is beta. We removed an HOH and we have this glycosidic bond here. Carbon 3 goes up. Carbon 4 goes down. This is carbon 5. This is the OH of carbon 5. And this is carbon 6. So this is sucrose. All right. Now, get it a little closer for you guys to see. Hopefully. You can always look these up in the book. They're all in the book. In your ebook, hard copy book, whatever, it's all there. Again, notice what's going on here. This was the potentially free aldehyde. This is your hemiacetal over here. It is hooked up in a glycosidic bond with carbon 2, this OH, that was the potentially free hemiketal. So these two guys are now stuck in this glycosidic bond. So the glycosidic bond of sucrose is not usually called alpha or beta. It's called like a 1,2 glycosidic bond, 1,2, or a 2,1 glycosidic bond. We don't normally give it an alpha beta terminology because looking at it this way, this would be alpha. Looking at it this way, it would be beta. So we just do 1,2. All right. Good. All right. So we are done with the disaccharide structures, and we're just going to jump right into the polysaccharides. There are all the polysaccharides that you need to know the structure of are all made up of thousands of glucoses, thousands of glucoses. So we're going to focus on amylose, cellulose, amylopectin, and glycogen. Those are the polysaccharides we're going to focus on. Now, amylose and amylopectin, the two of them together, that's what starches. So anytime you guys are eating a piece of bread or a potato or some pasta, you are eating both amylose and amylopectin. They are usually about every starch granule is approximately 3/4 amylopectin, 1/4 amylose, but you are eating both of those. Cellulose, like I mentioned earlier, is plant fiber. And glycogen, this is the way our body, humans, animals, store glucose in the muscle and in the liver. All right, so the next video is all going to be about the structure of these polysaccharides. So we will do that next.